Okay, so this is our third and final example of the many beautiful and fascinating mechanisms by which nature can transfer energy from one location to another, or transfer energy from one form into another. So in this case, we're going to be talking about electromagnetic energy, the flow of electromagnetic energy. So remember that fields are super important. So we already learned that, say, the electric field, the electrostatic field surrounding, say, some charged particles can store energy, stores energy in the space outside of those particles. And similarly, a magnetic field, say that around a bar magnet, can store energy in the space around that bar magnet. Now, if you put those two together, electric and magnetic fields together, in such a way that they move like a wave, then you have transport or transfer of electromagnetic energy. And of course, that's light. Okay, so that was figured out, of course, by Maxwell in the mid 1800s. So it explains things like, there's the sun up there, and the sun, energy from the sun gets to the earth and provides energy for life on earth. How does it do so? Well, by the transfer of electromagnetic energy, light. Okay, and so we're going to be talking a little bit about how that works. So I think this is of interest basically to all students of physics, and it's not that hard, and it's really beautiful. Okay, so, and it also underscores the importance of fields. Okay, so electric and magnetic fields can store energy, and they can also transfer energy, and this is a really cool mechanism. Okay, so we had the symbol W was used for work, force acting through a displacement, as a way of transferring energy. We also had the special symbol Q for the transfer of thermal energy, heat. Okay, we have a special symbol for the transfer of electromagnetic energy, which is S. Okay, and so S is the transfer of electromagnetic energy. Okay, so transfer of electromagnetic energy. And this is actually a vector. Okay, so it's the direction of the vector is the direction in which the light is moving. Okay, so now in high school, I'm sure you've all talked a little bit about light as an electromagnetic wave. So it involves electric field and magnetic field and stuff like that. And so we don't need to get into a whole lot of detail here. All we need to do is imagine the following. If we have light that's flowing this way, okay, let's take a point in space, say this point right over here. At that point in space, as the light goes by, at some instant of time, let's suppose that the electric field at that point is a vector that points straight up, like this. That's the electric field at that point in space, at that instant in time. Now, if light is flowing in that direction, if electromagnetic energy is flowing in that direction, and E is that way, then it turns out that there will be, I'll use a different color here, there will be a magnetic field at this point coming out of the board at me. So I'm drawing a three-dimensional picture here. Okay, so this is B. And then it turns out that you can figure out the rate, the intensity of the electromagnetic energy flow by calculating. So this S here is this vector. So S is the intensity of the transfer of electromagnetic energy. And how do you calculate that? Well, what you do is you just say, well, at that point in space, let's take the electric field vector. So this is equal to the electric field vector at that point. And we take the vector cross product with the magnetic field. So vector cross product with the magnetic field. Now, we talked a little bit about dot product. You can take two vectors and you can take the vector dot product to get a scalar. Well, there's also a vector cross product, which we're going to see a lot more about when we talk about angular momentum and torque and stuff like that. So if you don't remember what a cross product is, then just go look back in the first chapter of the book, sort of the review, the math review. Okay, so E cross B. So the idea is of the cross product is we just put our fingers in the direction of the electric field, and then we curl them in the direction of the magnetic field, and then our thumb points in the direction of the vector E cross B. So whenever you have two vectors in space, A and B, the vector cross product is a vector that's perpendicular to the plane formed by those two vectors. Okay, and in this case, the vector cross product of E and B is the direction in which the electromagnetic energy or the light is flowing. Okay, and now it turns out that there's there's a constant. Mu naught is called the magnetic permeability of the vacuum. It doesn't matter, it's just some constant, who cares? What we really care about here is the direction of the flow of the electromagnetic energy. Whenever you have in space, whenever you have an electric field, say in this direction, say a magnetic field in this direction, work out E cross B, and there will be flow of electromagnetic energy in a direction perpendicular to both E and B. Okay? Great. And so the dimensions or the units of this, if you work it all out, and this mu naught is required just to get the units and dimensions right, if you work it out, this is an energy per unit time per unit area. Okay, so what does that mean? So let's, unit area is the light is moving in this direction. Let's construct an imaginary plane which is perpendicular to the flow of light, and let's suppose it's 1 meter by 1 meter, it's 1 square meter of area. Okay, and so the magnitude of this vector tells you how much energy per second is flowing through, how much electromagnetic energy per second is flowing through that 1 square meter area, perpendicular to the flow of light. So it's very much like, if you think about sunlight, the intensity of sunlight is near this at the surface of the Earth is about 1,000 watts per square meter. So here, this is energy is joules divided by time is joules per second. That's watts. That's the amount of energy per unit time. Energy per second is watts. And the units for area is square meters in SI units. So this has the units of watts per square meter. So sunlight, when it's coming down at the surface of the Earth, is about 1,000 watts per square meter, which means that if I take a square meter solar panel or whatever, then in 1 second, that solar panel will see about 1,000 joules of energy, okay, if it absorbs all of it. Okay. So that's the idea, watts per square meter. Now, we don't need to get into a whole lot of detail about this. So all I need you to understand is that whenever you have an electric field and a magnetic field at the same point in space, there is flow of electromagnetic energy in a direction which is the vector cross product of E and B. Okay, very good. What else? Okay, so now what we're going to do is we're not going to apply this to something as complicated as light waves and this and that. What we're going to do is we're going to apply it to the simplest possible example we could imagine of transfer of electromagnetic energy, and that is the example of a battery connected to a light bulb with 2 wires. Okay, now when we do that, what we know happens is there is an electric current which flows through those wires, and in particular flows through the light bulb. Now we're thinking about the light bulb as an incandescent light bulb, which means it's a little piece of resistive wire, usually tungsten, because tungsten can get super hot before it melts. Okay, and so this is resistive. It resists the flow of electrons. So when electrons are pushed through this thing, there's friction, so to speak. We'll talk about this in a little bit more detail later. There's base friction, heats up, and then that piece of tungsten, that piece of metal, heats up until it is white hot. And that white hot piece of metal is made of positive and negatively charged particles. They're jiggling around really quickly, and so they're emitting thermal photons. Thermal light is coming off. Okay, and so that light bulb emits light, visible light, as well as heat, thermal radiation. Okay, great. So that's all whatever. The point is, clearly there is energy getting from the battery to the light bulb. And the question is, how? Okay, so now, you probably considered simple circuits in high school and stuff like that. And, there's this idea of, potential energy and this and that and whatever. All that stuff's basically nonsense. Okay, so I'm going to try to tell you what's actually happening physically, because it's really beautiful. Okay, and it's not that hard. Okay, you just need to think about it a little bit, but it's very beautiful. And it just relies on this idea of if you have electric and magnetic field anywhere in space, there's flow of electromagnetic energy. Okay, so we're going to draw basically a battery over here and a light bulb over here and connect it with two wires, and we're going to figure out how it is the energy gets from the battery to the light bulb. Okay, so in order to keep things as simple as possible, we want to find the simplest possible model of what a battery is. And the simplest possible model of a battery, simplest example of a battery, is a capacitor. Okay, and a capacitor is simply two metal plates. This is a metal plate, and this is a metal plate. Two parallel metal plates like this. Okay, initially these two parallel metal plates are uncharged, and there's no energy stored in our capacitor, no energy stored in our battery. So we're going to charge this thing up. And the way we do it is, well, by hook or by crook, at the end of the day, what we end up doing is we end up taking an electron out of the top plate and sticking it on the bottom plate. So now there's an extra electron on the bottom plate. And now all the positive and negative charges in the metal are no longer canceled. There's an extra positive charge here. Then you take another electron from the top plate and stick it into the bottom plate. Okay, and you keep doing that until you have a bunch of positive charges on the top plate and an equal number of negative charges on the bottom plate. And now our capacitor or battery is charged. And so what does that mean? Well, you know that if I have a positive charge here and a negative charge here, there will be an electric field which points from the positive charge to the negative charge. Okay, and so between this positively charged plate and this negatively charged plate, between the two plates, there will be a strong electric field. I'm going to draw this diagram pretty carefully because it'll get a little bit busy if I don't. Okay, so looks like that. And so there's an electric field E between the two plates of that capacitor. And as we talked about before, an electric field can store energy in space. That's basically how a battery works. It stores energy in an electrostatic field. Okay, and so what does that mean? Well, let's just remember what we talked about before. The idea is let's pick any point between these two plates, say that point over there. There is an electric field vector at that point, and what I do is I take the electric field vector at that point, I take its magnitude, I square it, and I divide by 2, and that gives me what's called the energy density. It's the amount of energy per unit volume stored in that electric field. Now, there's also, just like there's that constant there, there's a constant over here. Okay, we don't care about that constant. Basically, the square of the electric field divided by 2 is the energy per unit volume. Then I take a little cube around that thing. That's my little volume. I figure out the volume of that little cube, and I multiply by the energy per unit volume at that location, and I find the energy stored in that little cube of space, in the electric field in that little cube of space. And then I add up all of the electrostatic energy stored in all the little cubes between the plates, and I figure out the total amount of energy that's stored in our capacitor, that's stored in our battery, that's stored in the electric field between those two metal plates. This is a charged battery. Okay? And now we're going to take this battery and we're going to connect it to a resistor. Okay, so that means just a chunk of, say, metal, tungsten. Say, simplest example is in the form of a cylinder. Okay, so here it is. So there's a cylinder here, and then we're going to connect this battery to this filament of the light bulb. Okay, and then energy is going to be transferred from here, this region of space, to this filament. And the filament's going to heat up and it's going to glow and all that kind of stuff. Okay, so this is a metal plate on the top like this, and this is a metal plate on the bottom like this, and between those two metal plates is a resistive material, not very good at it, not a very good conductor. Okay, it resists the flow of electrons. So now I'm going to connect these two things together, the battery and the light bulb, and I do so by taking a wire. So there's a wire that I connect, a metal wire that's a good conductor. I connect it to the top metal plate, which is also a good conductor. Okay. I connect it to this metal plate. And then I go from the bottom of this battery or this capacitor. And I put another wire. Okay. Now I have a closed circuit. And so what's going to happen, we know, is there's going to be flow, there's going to be a current flowing like this, and which is really electrons flowing the other way, and then as I said, those electrons are going to heat up, because it's resistive, it'll heat this thing up, and so on and so forth. Okay, so now let's talk a little bit about actually how the energy gets from the battery to the light bulb. So there are several steps in this process, and they are quite beautiful and interesting. Okay, so the first step is, even before we connect this resistor here, okay, just imagine the resistor is not there, and we just had these two metal plates that are charged up, and then we stick two additional chunks of metal to it like this. Okay, then this is a piece of metal, and so is that. So if there's positive charges on this, there will also be positive charges on this piece of metal. And if there's extra negative electrons on this piece of metal, those negative electrons, I mean, they repel each other. And so they'll want to get as far apart from each other as possible. And so they will spread over the surface of both of this bottom wire. So there'll be a bunch of electrons spread over the bottom wire, and a bunch of lack of electrons or positive atomic nuclei left over on the top piece of metal. Okay, so the first thing is, when you set this thing up, I shouldn't even have drawn this thing. When you set this thing up like this, okay, there's no current flowing yet, but what there is surface charge. Okay, so I'll write that down first. There's surface electric charge. Surface electric charge, and it is static. Doesn't move around. Okay, so so we've got this battery. We attach these extra chunks of wire, and so those electrons will repel, and we will have this bottom wire has a bunch of electrons sitting on the surface, and there will be a lack of electrons on the surface of this chunk of wire, this chunk of metal, like this. Okay, so that's really, really important. So what that does, first of all, is let's look at this chunk of wire and this chunk of wire. We have a positive charge up there, and we have a negative charge down here. And so we're going to have an electric field from the positive to the negative charge. Or if we just look around this wire here, we're going to have an electric field in, say, up here, we're going to have an electric field in that direction. And say, at this point over here, down here, we're going to have an electric field in that direction. Okay, so it's like a positive charge, and the electric field goes radially out away from a positive charge. And similarly down here, we're going to have, this is a negatively charged region, and so there will be, at this point, there will be an electric field, which is pointing inwards towards the wire. And at this point over here, there's going to be an electric field pointing inwards towards the wire. Okay, so we're going to be interested in this point, this point, this point, this point, those 4 points. Okay, so right now there's no current flowing, and we've just got a static situation of static electric charge on the top wire, static electric charge on the bottom wire, and there's an electric field in the space surrounding these wires. If you were to look at this circuit from a side view, we have the cross section of the wires, say, a circle that is positively charged on the surface, and the bottom wire is a circle which is negatively charged. And so basically it's the electric field pattern of a dipole. So in the space surrounding these wires, there is an electrostatic field. Okay, so that's really important. That's the first step. So we get an electric field E. I should really write this out. E outside the wires. So this is E. Outside the wires. This is going to be a very important phrase which repeats over and over again. We're only thinking about the electric and magnetic fields outside the wire. Okay? Nothing about inside the wires. Okay, so the next thing is we hook this light bulb filament up here. So there's a metal plate on the top, and there's a metal plate on the bottom like this, and there's a piece of resistive material like tungsten sitting there. Okay, so as soon as we do that, now there's going to be current flowing. If that's the positive terminal of the battery, you know the current flows around the circuit like this. But you also know that really the particles that can actually move are electrons. So really it's electrons going from this negative plate flowing around inside the wires and through this resistor, and then to cancel out these positive charges. So eventually the battery goes dead. The electric field decreases to 0 and the battery goes dead. Okay, so so there's a as soon as we connect this resistor and complete the circuit, there is now a flow of current, which is really, instead of surface electric charge, it's a volume. electric charge. Okay, and this is actually not static, it's actually steady, it's actually flowing. Okay, so let's say that this is current flow. And so what we get is, so I'm sure you also know this, that if we have a, don't want to run out of room here, if we have a wire which is carrying an electric current in that direction, then you all probably know that that creates a magnetic field. That electric current creates a magnetic field in the space outside the wire. And so you just stick your thumb in the direction of the electric current and you curl your fingers, and that's the direction of the magnetic field. So there's a magnetic field outside that wire which curls around like this. So that's a B field. So there's a B field, a magnetic field, again, outside the wires, okay, which curls around. So if we look at, in this case, what we have is a volume electric charge. So there's electric charge inside the volume of the wire, which is moving. The current flows this way, so that means electrons are flowing this way. So there's, say, electron flowing this way, and, say, electron here flowing this way. Okay? Great. Great. Oh yeah, so then the current flows this way, and if there's a current flowing that way in a wire, then there's a magnetic field that circles around the wire like this. Okay, so if we go at this point over here and have a circle coming around, then at the top it's coming out of the page at me. So the magnetic field, we're using orange for the magnetic field, is coming out like this. And at this point, so it comes around like this, so at this point underneath the wire it's going in. It's going into the page, and so, you know, towards you guys. Okay, and so that's what's happening up there. There's also electric current flowing, you know, in the bottom wire in that direction. And so the direction of the magnetic field is this way, around the bottom wire. So at the top point, it's coming out at you. And at the bottom point here, it's coming out at me. Okay, so that's important. Okay, so now what we do is we say, okay, so now in the space surrounding these wires, we have electric and magnetic fields that are actually they're actually in perpendicular directions. So this situation is exactly like this electric field is up in this direction. This magnetic field is coming out at the board towards me. If I work out the direction of the flow of electromagnetic energy, well, I just go E cross B. E cross B is that way. Okay, so what that says is the static electric field due to the static surface charge, vector cross product with the steady magnetic field due to the current that's flowing around this circuit. E cross B is a vector which is in this direction. Okay, so this is the direction of electromagnetic energy flow, and it's flowing outside the wire. Okay, and if I do the same thing at this point down here below the wire, I will go E is this way, vector cross product with B is the same direction. It's towards the right like this. And in fact, if you go anywhere around that wire, you will find that there is electromagnetic energy flowing in that direction. It's most intense near the surface of the wire, and it decays as you go away, but it is energy, electromagnetic energy flowing on that wire. That wire basically guides the flow of electromagnetic energy outside the wire. Okay? Similarly, down here, we work out the same thing. And so some of you might be thinking that, yes, you know, electrons go around and then they get tired or whatever, and so somehow the energy there's lots of energy flowing here and then less energy flowing back and so on. It's nothing like that. Okay, so if we look down here and work out, well, what is E cross B down at this point, just above the bottom wire? Well, electric field is that way, magnetic field is that way, E cross B is in that direction. Okay, and similarly here, E cross B, you work out the vector cross product. E is this way, B is that way, E cross B is in that direction. And so what this is saying is you've set up this little circuit here. There's a static electric field due to surface charges on the metal, and there is a steady magnetic field due to this steady current flowing. And what it's saying is there's an electromagnetic energy flowing, being guided by the top wire in this direction. And in the bottom wire, there's electromagnetic energy flowing also in the same direction. It's not like this way, more this way, and less this way. They're both in this direction. Okay? Very important. The flow of current is in this direction in the top wire, and so is the flow of electromagnetic energy. The flow of current in the bottom wire is that way, but the flow of electromagnetic energy is that way. They're both to the right towards that battery. Okay, it's nice. Ooh, hang on. This is kind of weird. What's going on here? Okay, well, so this is really cool. So it turns out that, just as, when you have a wire that carries electric current, there is a magnetic field around that wire. Well, inside a capacitor, when you study electromagnetism a little bit, you'll understand that this decreasing electric field, because as the battery discharges, and these negative charges cancel those positive charges, a decreasing electric field will create a magnetic field. And that magnetic field, what is the direction of that magnetic field? Well, the direction of that magnetic field is it circles around. So if we go in the space of the gap, we have two metal plates. There's a gap around it. So in the gap around it, let's draw a little circle, just sort of outside that gap over there. The magnetic field is in, let's get this direction right, the magnetic field is in this direction. Okay, and at this point, the electric field is down. So just at the gap there, the electric field is down. The electric field is down, and the magnetic field is in that direction. So if we work out the vector cross product, whenever we have an E and a B field, we just work out E cross B. That tells us the direction of the transfer of electromagnetic energy. So here, E cross B is in this direction. It's radially outwards. And if you work it out anywhere in the gap of this capacitor, it's radially outwards. Okay, great. So what actually happens is when you have a battery connected to a light bulb like this, the energy, the electromagnetic energy, flows out of the sides of the battery. If a battery has a metal top and a metal bottom, it doesn't flow through there. It flows out the sides of the battery. If you were to encase the battery, in metal, okay, you'd basically short circuit the thing. It doesn't work. Okay, so the electromagnetic energy flows out of the sides of the battery into space. Okay, and then if you work out E cross B everywhere and so on, you'll discover that near the top here, the electromagnetic energy flows out, and then it flows over the top of the battery, and then it flows along the bottom of this wire like this, and it ends up basically coming to that resistor. Similarly, at the bottom here, we have electromagnetic energy flowing out like this. It flows outside the bottom of the battery, and then it is guided by the wire, and it flows in this direction towards this resistor here, towards this tungsten filament that we're heating up. Okay, and so basically, it's just remarkable. This electromagnetic energy flows out of the sides of the battery, is guided by those wires in this direction, both in this direction toward that resistor. Okay, and then we say, well, what happens at that resistor? Well, so this is so cool. Okay, so we have electrons. There's current flowing, right? Current flows this way, electrons flow this way. So electrons are flowing this way, trying to get from the negative plate to the positive plate. Okay, but in here, there's very little resistance to the flow. When they hit the resistor, there's resistance to the flow. And so what happens is negative charges build up. They build up in this region of this bottom plate. And then there's a depletion of electrons here, so there's extra positive charges build up over here. Okay, so now you have sort of exactly the same situation here as you have here. And so there is an electric field inside that filament. Okay, and it just goes immediately outside the filament like this. So there's basically an electric field between the top and the bottom of the resistor, which is going down like this. Okay, so what does that electric field do? Well, if you think about it for a second, there is electric current flowing. The electrons move this way, the electric current is this way. Okay, so looking at that picture over there, I put my thumb in the direction of the electric current, and there's a magnetic field that circles around that resistor in that direction. Okay, so let me draw that thing. So that's in this direction, it goes around like this. Looks like that. And so, say for instance, at this point in space over here, the magnetic field is into the board towards you guys, and the electric field is down like this. And if you work out, what is the direction of the flow of electromagnetic energy? Well, it's E cross B. So I go E cross B. Oh, that's radially inwards. Okay, it's radially inwards. And if you do this same calculation anywhere around around that resistor, you will find that electromagnetic energy flows radially inwards all around the resistor. So this is completely remarkable. What happens is the energy stored in the electric field between those two plates, when you hook it up and there's an electric current flowing, so now there's both electric and magnetic fields, you can have E cross B, then energy flows out the sides of the battery, is guided by that wire, and then it flows in to the resistor from the outside in. Okay, so it goes like this, and then it flows in from the outside. Okay, so that's how electromagnetic energy gets from the battery to that resistor. Okay, and so so I just want to sort of emphasize that point because that's really quite remarkable. So third point here is that we work out, well, what is the intensity of the flow of electromagnetic energy. Well, we work that out, so that's 1 over mu naught E cross B. And if we work it out everywhere around this wire, we see that this is energy flow outside the wires. Electromagnetic energy flow outside the wires. Okay, great. Okay, so now you say, well, wait a minute. I kind of have this impression that these electrons, they're moving and they have some kind of kinetic energy and so on. And somehow when the electrons, they move very freely through this wire, and then they hit some resistor, and there's resistance to their motion. And really what that is the electron hits some impurities in the material, roughly, and bang, and in the simplest case is it goes bang and it comes to rest. And so what it does is it transfers, the electrons have kinetic energy, for sure, okay, and then they go bang and they hit an atom or a molecule or impurity in that resistor, and they come to rest. And so they transfer their kinetic energy to atoms in the tungsten wire, in that tungsten piece of wire. And so the kinetic energy transferred to those atoms, it heats up those tungsten atoms. And so they start jiggling more and more vigorously. They heat up until this thing becomes white hot and then starts emitting thermal radiation. Okay, electromagnetic radiation, thermal radiation. Okay, and so that's what's happening inside this thing. Okay, so it is true that yes, this thing is being heated up by the kinetic energy of these electrons. But now here comes the most interesting part of this. So finally, just to sort of complete the whole argument here, let me look at an electron that is inside this. Okay, can I do this? Let's put it here. This might get really messy. So here we have an electron which is making its way through that resistor. Okay, and so what it does is it's got some kinetic energy to begin with. Bang, it hits an atom in the tungsten, it gives up its kinetic energy, and it comes to rest, let's say, simplest case. Okay, so, but now it's got to keep going, okay, because there's this current flowing. And it can keep going. How? Well, because there is an electric field inside that resistor, which is in that direction. And so that electric field exerts a force on positive charges in that direction. It exerts a force on negative charges in that direction. Okay, so there is a force acting on the electron inside there. And so it will take the electron that was at rest and it will force it to accelerate and pick up speed again and keep on moving through. Okay, so the electric field inside gets it going again. But the most interesting question now is, well, sure, I can understand that, yeah, that electric field, makes that thing speed up. But where does the energy come from to speed that electron up again from 0 to some speed? You got to transfer kinetic energy to that thing. How does that work? Well, that comes exactly from, that's what the electromagnetic field energy is doing. It's replenishing the energy, the kinetic energy lost by those electrons. Okay, so they lose energy and they give it up to the tungsten atoms to heat it up. Okay, but then they need to be re-energized again. That energy comes in from the outside of the resistor, and that's the role of the battery, is to do that. Okay, so that's pretty cool. So inside the resistor, the electron gives up its kinetic energy, turns into thermal energy, and the electric field inside accelerates it, but the energy required to accelerate it comes from the flow of electromagnetic energy, which ultimately comes from the electrostatic energy stored inside the battery flowing around like this. The wires guide the flow of energy outside the circuit. Okay, so I wanted to sort of give you this example because A, it's super cool and fun to talk about, and B, it really shows you a great example of the importance of fields. Okay, so the electric field inside this battery, where do you think a battery stores its energy? It's in the electric field. Okay, and if you have electric and magnetic fields present, then not only can you store electric energy, store energy in electric field or store energy in magnetic field. If they're both present, so you can have an E cross B, then you can also have transfer of electromagnetic energy from one location to another. And in the case of this circuit, that electromagnetic energy is guided by the wires. In the case of energy getting from the sun to the earth, there are no wires. Okay, and these are just flowing in free space. Okay, you have electric and magnetic fields in free space, and they flow as a wave. Okay, and so it's actually required to be like a wave. This is just a DC circuit. Okay, but it's exactly the same principle. So energy gets from the sun to the earth by exactly the same principle as energy gets from the battery to the light bulb. Okay, it's through this E cross B mechanism. That's one of the most beautiful things about physics, is once you understand some basic fundamental thing like this, it applies in a huge number of circumstances and allows you to understand a tremendous amount about what's going on, how nature works in the world around us. So very, very beautiful. So anyways, this is another awesome example of one of the mechanisms whereby nature can transfer energy from one location to another. Fields matter. They're real. They're important. Okay. In order to really understand sort of anything about energy, you need to understand a little bit about relativity, E equals mc squared. You need to understand a little bit about fields. Okay. So hope this example was fun and illuminating and interesting.